Hello everyone, my name is Max Weber and today I'm gonna present you our work on white box performance influence models, a profiling and learning approach. Today, almost all software systems are configurable. Configuration options enable the user to customize the software system to their needs. However, the configuration space might be really large, depending on the number of configurations. If we want to know now whether some configuration leads to a fast execution time, or whether there is a better configuration, we need a performance model. With such a model, we get the performance of all possible configurations. This model has 2 to the power of 3 possible different configurations. Without such a model, we would need to measure all the configurations to know which one is the best. But this is usually infeasible. As another small example, imagine a system with 33 binary configuration options. With such a system, we could generate more different variants than there are humans on the earth. Here in the lower left corner, there are software systems that we used for evaluating our approach on. We see here databases in which you can configure, for example, different filters, compression algorithms, and optimizations. We see rendering engines, static source code analysis tools, and rasterization tools. All these software systems have configuration options that together form a configuration space. Sampling strategies are used to select a subset of configurations. This set should be selected in such a way that it is representable for the whole configuration space. Next, performance is measured for all configurations. That is, the software system gets executed under a specific configuration and measures the execution time of the system. The next step is then to use machine learning to learn the influence of the configuration options and their interactions on the execution time of the system. This then results in a performance influence model. Such a model usually has a base value independent of configuration options and add or subtract values based on the individual options that are enabled. And with these models we can then, for example, optimize configurations or predict unseen ones. There are different ways of how properties of software systems can be modeled. On the one hand, there are the black box approaches. Here, the execution time is measured from the start to the end of the program. This approach has a high accuracy and low measurement effort compared to the other approaches. But we have no details of the internals of the system, and we don't know where in the source code a feature, that is a configuration option or interaction, has a performance influence. On the other side, established white box models show these internals. We can see here at the line or even at the statement level where a feature has an influence. These models enable root cause analysis, that is, searching for a configuration-related performance bug and pinpointing to specific code regions. But these models usually do not scale very well, even with medium-sized configuration spaces, because they usually rely on costly static data flow analysis to identify feature regions. Our solution now is to combine both sides into method-level white box performance influence models. The goal here is to have one performance influence model per method of the system. We don't need the expensive static analysis because we simply measure every method that gets executed using a profiler. What can we use these method-level models for? First, we know the configuration-related variants of the methods, such that we can detect those methods that strongly react to changes in the configurations. We found out that most methods have no or only a small variance. That means that the execution time of those methods does not change because of changes of the configuration options. There's also a small portion of methods with a high variance. These methods are the key driver for configuration-related performance changes. Method-level models also show the share of the individual configuration options on performance. We can see the distribution of the feature influences on a method of the system PMD. Many of the features don't influence the execution time of the individual methods at all, and only some features have a high influence. We can see this behavior in all of our subject systems that we tested our approach on. So, applying our approach, one can identify methods and features. How does our approach work? We start with a set of configurations that we select from the whole configuration space. Now we measure the performance of each method that is executed under the configuration. Therefore, we use a profiler, here Java Interactive Profiler. This profiler outputs the total execution time of all executed methods. If we have profiled the system with all configurations, we use machine learning to learn one performance influence model for each method. These methods show which configuration option or interactions are influential. We can then again predict execution time of unseen configurations. But it turns out that some of these methods could not be learned accurately. Therefore, we select those methods that could not be learned accurately and that have a share in the overall performance. And then we add another step where we profile again with a fine-grained profiler. Kika measures the execution time of each individual method execution. This way, we concentrate on those methods and reduce the measurement overhead. After this, we proceed as before. We utilize machine learning to generate the method-level performance influence models. With this additional effort, our approach is able to model the performance of almost all methods accurately. We did a variance analysis prior to the development of our approach. We identified 3 different types of variance. The figure shows the distribution of all method calls of one method that is executed under one configuration. We call this method context variance because it is the method context that is responsible for this distribution. The method context can be global variables and method parameters. The performance of a method is then the accumulation of all execution times of the individual method calls. Using the fine-grained profiler, we are able to reveal this distribution. Unfortunately, there are huge outliers in the execution time of individual method calls. These outliers cause an increase of the method's execution time. By filtering these outliers, we are able to improve the results. Changing the configuration of the program changes the whole distribution. This is the type of variance we can learn in our performance influence models. And the last type of variance is the measurement variance. It is shown by the differences between the distribution of the different rows. This variance depends, for example, on the measurement system and concurrent running processes. Knowing this is important to estimate the measurement noise. This is especially important in a white box setting in which the profiling process might significantly cause such measurement bias. Here we see the accuracy of our white box performance influence models. Each box plot shows the prediction error of the methods of the software systems. We compute the error by predicting the execution time of 100 randomly sampled unseen configurations, and in the end we got pretty good results. Most of the method models got less than 5% prediction error. And after applying the fine-grained profiler, our approach is able to learn almost all methods accurately. Currently, we are working on a prototype which visualizes our method-level performance influence models. This prototype is implemented as an Eclipse plugin. The user selects a configuration, and the plugin colors all methods according to the predicted execution time of the method models. This way, the user is able to compare the effect of different configurations on the execution time of the methods directly in the IDE. This may help developers in identifying performance-relevant methods. We are now at the end of my talk. Thank you for your attention. Feel free to contact me via mail if you have any questions, or visit the supplementary website if you want to get the performance data or the implementation. Now I'm open for questions.
Thank you. Hi, everybody. Welcome to this session on performance modeling of highly configurable software systems. My name is Carolyn Seaman. I'm from UMBC, which is in Baltimore in the United States. And I have Max with me, whose presentation you just heard, who is ready to answer your questions. So while you're thinking about your questions and writing them in the chat, which I hope you do, I will start off with one of my questions. And Max, I was wondering, once you have the tool implemented at the very end of your talk, you talked about a tool as the next steps. Once you have that tool implemented, that gives you some opportunities for fuller evaluations of your approach in practice. Can you say a little bit about what those evaluations might look like, how you would go about evaluating your approach in practice using the tool?
So yeah, the tool in the end was to like show the values of the methods of the performance influence models per method in an IDE, so that like programmers are able to check their current configuration that they have for their software system, in comparison to the other methods. So you get a list, like an overview list, which methods consume the most execution time, and you can also imagine of having other models like energy models and see which methods have the highest consume the highest amount of energy. And then we plan to show this to like programmers and practitioners and see if they can can find something out with this.
Okay. So you would ask them if that information is useful, or if it allows them to do something differently than they would do before, right? So
because for things like bug detection or so, we can provide them with an ordered list of possible methods that are possible reasons for like performance bugs or energy bugs. So the programmers exactly know with the actual current configuration how many time they spend in the method, so we can find faster bugs maybe.
So you envision people using this during testing or earlier in the process? Like
so the process of generating or learning these models is needs some time. Like you need to profile the system and so on, and then you need to learn the models. And we imagine that after a day of programming or so, the models can generate it overnight or so, and then at the next day the programmer can like see how the programming process evolves, how the methods that they wrote the last day, how they improved or degraded in terms of performance.
So does this information help them take corrective action? Like if they don't like the results that they see, does it help them decide what to do next to make it better?
Yeah, so at a level of methods, yes. So they see, okay, I need to focus at these methods, and then they can go from these methods on, like exploring the that are called, and have a start point where they can search for bugs.
Okay. All right. So our audience still doesn't have any questions in the chat, and I don't have any others. Is there anything else you'd like to add, Max, that if you had had a couple more minutes in your presentation, you would have added?
I think no.
Okay. All right. Well, then we'll end it here. There will be the second paper in the session. The presentation will start in about 6 minutes. So stick around, and I'll be back with the next author for the Q&A after that. So thank you very much, Max. There will be a discussion room that will pop up in 5 minutes and 40 seconds. So if you'd like to talk with Max one-on-one or close to one-on-one in the discussion room, be sure to watch for that pop-up discussion room to come up then and click on it. All right, Max, thank you, and take care. Enjoy the rest of the conference.
Thank you.